everybody was wilding out. Ish was going crazy, and he looked at me, and I looked at him, and I was like, dude, you say one more thing, you know it's gonna happen. You know it's gonna happen. And then he looked at me right in the eyes, and he said, it's time for science. So yeah, today we're talking about science. Specifically, we're gonna be talking about scientific notation. And we use scientific notation for things that are blank or blank. Take a second, what do you think those blanks are? Maybe you've heard of scientific notation before. Well, I'm glad you thought about it. Scientific notation we use for things that are very, very big, or things that are, very, very opposite of big, small. Wow. So if I'm trying to describe something that is super huge, probably larger than my pitiful mind can comprehend, or super small, then I like to use scientific notation. Let's talk about some examples of where that might come into play. Check this out, check this out, check this out. So in here, believe it or not, is flour. I'm not going to troll you like that. And flour is this very, very fine substance. I've already got a ton of flour on my finger, and there are so many individual little particles that make up this flour. If I were to say, hey, how many of these little bitty grains are there in this flour, it would be a huge number. And when we have big or huge numbers, scientific notation comes into play. Forget the flour, we can also talk about this big, beautiful sodium chloride barrel. And inside here, it's not a barrel, it's a bucket. But inside here is sodium chloride. And if we look at our sodium chloride, if we look at it, let me come over to you. Look at our sodium chloride. We know that it is made up of individual little cubic granules. So I might ask, how many granules of sodium chloride are in this whole bucket? And so, we could probably write out an answer for that. But I think I would get really irritated writing out that answer. Because as I try to write out the number of particles that are in there, it's gonna take me a while. I'm gonna assume there's probably more than 1,000, probably more than 1,000,000. There might be more than 1 billion in there. Heck, there might even be more than 1 trillion, though that starts to seem like a stretch. But already, I've wasted time writing all these zeros. And if I wanted to keep this all nice and concise, that makes me angry, because it's big and long and ugly. And with scientific notation, we can write this in a much more concise fashion, in a smaller, more cute, simplified way. So instead of writing 1 followed by this many zeros, what is that, 12 zeros? I could express this as 1 times 10 to the 12. And look how much less space that takes up. Isn't that nice? Isn't that nice? You don't have to count zeros too. So let's imagine an even larger number. Let's say we wanted to talk about an even bigger number, like how many miles it is to our nearest galaxy. The Andromeda Galaxy is some number of miles away. It is 1, 4, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think that's enough zeros. It's that many miles away. I don't even know how to say the name for this number. It's such a big number. But scientific notation gives us a nice, easy way to do this. I'm going to put in some commas just so I can see how many groupings of 3 dudes I have. This should come out. I should be able to express this in scientific notation, rather, as a nicer number, as 1.491 times 10 to the 19th miles. And look how much nicer this looks than this big old chonker right there. This is where we use scientific notation, not only to save space, but when I look at this number, I literally have to count the zeros. And if I make a mistake counting the zeros, then that could screw up any other math I do using this number. Here, this number 19, this exponent, helps tell me how big the whole number is. And we'll talk about how to actually understand that in a second. But let's look at one more example. If I want to talk about something teensy tiny, like the size of a carbon atom. You and me, we are both carbon-based life forms. Unless you're an alien watching this on a transmission planning to exterminate all life on Earth. Please don't. But otherwise, we are both carbon-based life forms. And one atom of carbon is 6.63 I'm going to write out the scientific notation first. 6.693 times 10 to the negative 9th inches. Now this guy's a little bit different because on these first two examples we have positive exponents. When we have a negative exponent, like we do here, we're going to get a number that's very small. So we said scientific notation is things that are for big things and small things. These are both big numbers, but here we're going to see a small number. So in this case, this number should be a 1, 2, 3, 4, 5, 6, a little number like this. There are very few inches in the diameter of a carbon atom. They are hecka small. That is a very small number. And again, you can see that it's kind of easier to look at this number than this. Because when I look at this number, at least I don't have to do any counting. When I look at this number, I have to do some counting. And if I wanted to punch that in on a calculator, I can easily hit the 0 button one time extra or one time not enough. And yeah, it's just more likely that you're going to make mistakes. So it's important that we not only know what scientific notation is, but also how to use it. So let's talk a little bit more about how we're going to use it. So let's do a little bit of defining terms. When we are using scientific notation, there are two terms that we should know so that we understand them. And those two terms are coefficient and exponent. Whenever we write a number in scientific notation, we have a coefficient. This is a value between 1 and 9.99999. And we're going to multiply that times 10 raised to a power. This exponent tells us, do we have a number that is very large, or do we have a number that is very small? Like I said just previously, when we have a big number, we have a positive exponent. So this would be a big number because the exponent here is positive. When we have a small number, we find a negative exponent. So if I decided to just go ahead and put a negative sign there, now all of a sudden this is telling us about a very small number. Let's talk about how we're going to convert from regular old notation into fancy pants scientific notation. The way I'm going to do it is I'm first going to get down my coefficient. So like I said, the coefficient is always a number between 1 and 9.999. Here I'm going to take my last non-zero digits, or rather all my non-zero digits, and convert those into this coefficient. Since there's only one non-zero digit here, and it is the number 5, 5, which is between 1 and 9.999, will be my coefficient. So then I'll add in my times 10, and now we need to get the exponent for this. The way I'm going to get the exponent is I'm going to count from my largest non-zero digit. This guy is the biggest non-zero digit. It's in the largest place, the furthest over in this direction. And I'm going to count from there to the ones place. So how many jumps do I have to go from here to the ones place? I have to jump 1, 2, 3, 4, 5, 6, 7 times. 7 will be my exponent. And just like that, I've converted this big old stanky boy into a nice little cutie. Let's do this one as well. Here we've got two non-zero digits. So both of those should get included into our coefficient. But again, our coefficient can only be between 1 and 9.999. So I can't make my coefficient 45. Instead, my coefficient is going to be 4.5. How cute. And I'll put in my times 10 as I do. And now I'm going to, again, count from the largest digit, the digit that is in the highest numeric place. And I'm going to count from there to the ones place. So it takes me 1, 2, 3, 4, 5 jumps to get to that ones place. So my exponent here will be a 5. Let's blaze through these other dudes real quick. My only non-zero digit here in this small number is this 5. And I want to figure out what the exponent of it is. Well, my exponent should be negative because this is a small number. It is not a larger than 1 big number. But I'm going to follow the same rule. I'm going to count from the largest non-zero digit. In this case, this is the largest or highest value non-zero digit. And I'm going to count from there to the ones place. So it takes me 1, 2, 3, 4, 5 jumps to get to that ones place. So now my exponent is going to be negative 5.
Wow.
Negative because it is a small number. 5 because I had to make 1, 2, 3, 4, 5 jumps to that ones place. And let's look at this last example. Our non-zero digits are this 5 and 6. I don't want my coefficient to be any greater than 9.99, so I'll make my coefficient 5.6. Okay, cool. And I'll do the same thing. I'll count from the largest number, the number that is in the highest value place. So 5 is in a larger place than 6, so I'll count from 5 to that ones place, and it takes me 1, 2, 3, 4, 5, 6, 7 jumps to get there. So my exponent should be negative 7. Cool beans. Why don't you pause the video real quick and try converting these two beautiful babies into scientific notation. Pause it. Give it a shot. Meow. Sick. You tried it out. Well, let's go through it together. I love you. So, I'm going to start off by writing my coefficient. 6 is the only non-zero digit here, so we'll just put in 6. Okay. And then I will add my times 10, and I got to figure out the exponent. We'll count from the largest non-zero digit, the largest value place to that ones place. So 1, 2, 3, 4, 5. Okay, 5 jumps, not too spicy. 6 times 10 to the 5th. And if I wanted to tackle this guy, well, I'm going to start with the coefficient, 4. 4 is the only non-zero digit present. And I can do 4 times 10, and what is my exponent going to be? Well, I'll count to the ones place. So I make 1, 2, 3, 4, 5, 6 jumps there. So this is going to be 4 times 10 to the negative 6. It's very important that I remember that negative symbol, because that tells me that this is a number that's less than 1, smaller than 1, and not a number that is far larger than 1. Wow! Wow, wow, wow!
Wow.
All right, so let's look at a few examples of converting from scientific notation into regular notation. So, if I want to do that, I'm basically going to reverse the process I did. And so if you recall, I started off by jotting down my coefficient and then popping in some zeros. So I can kind of do a similar thing here, but actually I'm going to jot down my coefficient first again. And I can tell that this is going to be a small number, so I'm going to put my 9, 4, 1 over here. And I know that there are 8 jumps between this 9 and the ones place. So I guess I could just go from the 9, I need to make 1, 2, 3, 4, 5, 6, 7, 8 jumps. And so now this should be the ones place. Cool. Cool beans. That's kind of why you heard me at the beginning of the video, counting stuff out. Well, let's look at the next one. If I want to convert this dude into scientific notation, rather regular notation, it's already in scientific notation. So I'm going to jot down my coefficient first. I'm going to leave out the decimal point, just like I did here. And I'm going to say, okay, between this 7 and the ones place, there should be 4 places. There should be 4 jumps. So from 7, I jump 1, 2, 3, 4 times to get to that ones place. Let's look at that with my red marker. Just count out these jumps. So I started off at 7, and I jumped 1 time to that first one. I jumped another time to that one. I jumped a 3rd time to that 0, and I jumped a 4th time to that one. Neat. Why don't you, dude, try out these 2 puppies right here, and we'll go through them together. Okay, cool. You tried them out. Let's go through them together. So I'm going to start off the same way. I'll jot down my coefficient first, and I will leave out the decimal point. And then I'm going to say, all right, this is going to be a big number because this is positive. A positive exponent means a big number. So I know that there's going to be 9 jumps, 9 places between this 3 and the ones place. So from that 3, I go once to the 5th, to this 5, and then 2, 3, 4, 5, 6, 7, 8, 9. That should be the ones place. And I can put some commas in here to make this number look pretty. So pretty. So pretty. Let's try this one. We know that it's a small number because we have a negative exponent. So I'm going to start off by writing down my 4, 0, 0, 2. And 4 is going to be the biggest number in here. So counting from that, it's going to have the largest place value, I guess. But counting from there, I'm going to make 6 jumps to get to the ones place. So here I need to jump once, twice, 3 times, 4 times, 5 times, 6 times. This should be the ones place, so we'll put a little decimal after it, and here is my beautiful number in regular notation. Oh, even though it's more beautiful in scientific notation. Wow, wow, wow. Wow. Wow! Wow? Well, dudes, I'm going to try and keep this one short. So, I hope you learned a bunch about what the fridge scientific notation is, and I hope you feel like you're totes ready to deal with some big old honking numbers like in astronomy, or some teensy numbers like in physics and particle physics and in chemistry, and I hope you have a great rest of your life. If you liked this video, maybe go and boop, boop, boop on that like button, maybe go and boop, boop, boop on that subscribe button, maybe go and Venmo me 20 bucks, I don't know, ta-ta, have a great rest of your life.